Afternoon, everybody, and welcome to Deploying Bus Bypasses in Dense Congested Cities. My name is Stephanie Lewis. I will serve as your moderator today. And before we get started, I'd like to just introduce our presenter. Our presenter today is Nadav Branicki. He is a PhD candidate in the Department of Civil and Environmental Engineering at the University of California, Berkeley. His research focuses on traffic operations in congested urban environments, with an occasional emphasis on improving transit efficiency. He is a member of the TRB Standing Committee on Bus Transit, and he holds a Bachelor's of Science degree in Civil and Environmental Engineering and a Master's of Science in Transportation Engineering, both from UC Berkeley. So with that, Nadav, take it away.
All right. Okay. So good afternoon, everyone, or good morning for those of you, as I am out here on the West Coast. My name is Nadav Branicki, and today I'll be presenting a study on deploying bus bypasses in dense congested cities. This study was conducted in collaboration with Dr. Jean Doig and Professor Michael Cassidy, who are both, I believe, on the call. Our study explores where these bus bypasses should be placed in a congested urban network, in a congested city, with the objective of reducing bus travel times, of speeding up buses. This is especially important during the peak hour, when spillover queues tend to grow long. These queues might originate from a few bottlenecks, from the network's critical bottlenecks, which restrict its capacity, but they grow, they spill over to fill many links. This produces a state called hypercongestion, in which these spillover queues interfere with network circulation and block cars from proceeding through green lights. As a result, fewer trips can be completed, and the overall performance of the network is degraded. This hypercongestion isn't just a problem for cars. It also slows down buses that share lanes with cars. This is called cross-modal interference. Anything that adds delays to cars will also add delay to buses traveling in shared lanes with cars. This means that as we try to help buses, we have to be mindful of how we slow down cars. Any added car congestion is going to adversely affect buses. This is why we don't look at a couple of traditional interventions, starting with signal preemption. It might seem very helpful to give a green light out of turn to an approaching bus. It would speed up that bus, but doing so would disrupt the broader signal cycle, thus delay car traffic, which in turn will delay the buses that come after. It would be possible to eliminate cross-modal interference altogether by building a lot of dedicated bus lanes. In theory, you could achieve this by placing a bus lane on every hypercongested link that buses use. But that is often very impractical in a dense city, where road space is limited. A bus lane can typically only be deployed by taking a lane away from general traffic. This would harm the already damaged car flows, which the buses might be insulated from, but decision makers would not. This is politically very difficult. Any attempt to deploy bus lanes, but only selectively, on only the handful of most congested links, would be the worst of both worlds. It would still cause a harmful cross-modal effect by increasing delays on the other hypercongested links that don't get a bus lane, and at the same time it would also cause political outrage. This brings us to bus bypasses as a sort of middle ground solution. They are a measure that provides buses with some exclusive space, and some help getting through a signal, as I'll explain shortly. A bypass, at its most basic, is a lane segment that lets buses skip ahead of the queue at a light during a red, as you can see in this image. The specific design we test, which is shown here, is taken from AASHTO's Transit Facilities Guidebook. It avoids the political problem of harming cars because it doesn't take a lane away from car traffic. Instead, the bypass might repurpose an existing right turn lane, in which case right turning cars would continue to use it. Alternatively, it could be set up by taking away a small amount of curbside parking. This design also operates within the confines of the existing signal cycle to avoid disrupting signal coordination. During the first 5 to 10 seconds of the usual green phase, if a bus is present, a special bus signal will give that bus an early start, while cars are held back by a red. This allows the bus to move freely into the travel lanes downstream. After that 5 to 10 second increment, when the bus has gone through, all lights will show a green to let cars proceed. AASHTO's guidebook recommends that a near-side bus stop should be placed in the bypass, since the bus will be dwelling there anyway. That makes a lot of sense. We adopt it in our study. This sounds nice, but our experiments will show that not every hypercongested link is necessarily the right place for a bypass. We find that there are some locations where bypasses fail to help buses, or even harm them, as we will explain later. But to explore the bypass's benefits, or as it were its disbenefits, we need to model the network without a bypass. When we remove the bypass, the near-side bus stop remains, and we look at two placements for it. The first is an inline stop. It is the least costly and the least space-consuming. At an inline stop, buses dwell in a travel lane while passengers board in the light. By occupying a lane, buses obstruct car flows. However, one would expect this to be pretty favorable to buses who can proceed in and out of their stops with ease. Our findings will show, however, that these inline stops can be bad for buses and not just for cars, in the same circumstances that make bypasses ineffective. As an alternative to inline stops, we will also consider offline stops. At these, the bus enters a pullout outside of the travel lane to serve passengers, which thus leaves car flows unobstructed. However, after it is finished serving passengers, the bus has to merge back into the busy traffic stream with no help. We would expect, therefore, that the offline stop should be quite bad for buses, but pretty good for cars. We will show, however, that the offline stop is, in some cases, the best treatment for buses as well. To conduct all of this analysis, we need a site. We use an idealized one-way urban arterial. This site reflects what we deem to be the essential characteristics of a city street network, but it is deliberately very simple. Simple enough to isolate the impact of the three treatments that we study. This arterial is 2 lanes wide, with cars and buses sharing both lanes. Each of its links is 120 meters long, which reflects a dense downtown setting. When present, bypasses are 75 meters long. The arterial is 15 links long, with those links numbered in ascending order going upstream. That same numbering scheme is used for the 15 intersections, all of which are signalized. All these signals are coordinated using the zero offset scheme, which means that they change simultaneously, a strategy that is known to perform well in congestion. In the name of simplicity, we don't consider any turning traffic. This means that all cars and all buses traverse the full length of the arterial. We place a bottleneck, the critical bottleneck of this simple network, at the downstreammost intersection, intersection 1. The capacity of this intersection restricts the discharge flow of the arterial. Queues originate from here and propagate upstream to fill many links. Link 1, being the closest to the critical bottleneck, is the one where queues will form first and where they will persist the longest, which is why we study link 1 first. It is a high leverage location. The network is sensitive to changes that are made here. And so we place a bus stop on this link, near side as per AASHTO's guidance, and treat it in 3 ways. We consider the offline stop, where the bus enters a pullout, an inline stop, where the bus dwells in a travel lane and obstructs cars, and we consider, of course, the bypass. Our intuition tells us that the bypass could be really effective near the bottleneck. Because queues form here first and persist here the longest, the buses might get the most use out of it. We're not alone in this thinking. Reports from the practice suggest that bypasses are often placed deliberately at bottleneck locations. The AASHTO guidebook, which is very specific on many aspects of deploying these bypasses, doesn't advise against this kind of deployment. We find that it should. Our findings show that a bypass should not be placed on this link so close to the critical bottleneck. You might find this to be surprising or even counterintuitive. I know I did. So, after I present our numerical results for treating link 1, I will explain the mechanism that causes this counterintuitive finding. Those numerical results show that the best treatment for buses is in fact the offline stop, where they use a pullout and have to merge back into traffic with no help. With the offline stop deployed, buses take an average of 14.1 minutes to traverse the entire arterial. Cars are naturally a little bit faster, at 12.5 minutes. The inline stop is a full minute worse for cars. This in itself is not surprising, as each bus blocks car traffic while passengers board in the light at the stop. But, more notably, the inline stop delays buses almost as much as it delays cars. The bypass works out similarly. It predictably harms cars, but it surprisingly fails to help buses. If we generously assume that 5 seconds of exclusive green is always enough for buses to exit the bypass, we find that bus performance is unchanged, unimproved, relative to the offline stop, while cars are 0.6 minutes worse off. Performance for cars is worse still if we assume, performance for cars and buses is worse still if we assume conservatively that buses need 10 seconds to exit the bypass. Under this assumption, the bypass not only fails to help buses, it delays them by 1.5 minutes relative to the offline stop, while delaying cars by over 2 minutes. I think this is quite perplexing. Offline stops force buses to merge back into traffic with no help and give them no appreciable direct benefit. So we would expect them to be the worst for buses, and yet they turn out to be the best. The reason for this is cross-modal interference caused by something we call voids. We can understand them by looking at this time-space diagram with the signal of intersection 1 indicated by the green and red bars. When the special bus green is activated, indicated by these gray bars, it holds cars back. This creates a void in car flows. That void travels through the bottleneck and starves it of cars. As a result, the arterial's total outflow drops, and queues upstream grow longer. Buses get stuck in those queues too. Whatever time buses save thanks to the bypass is completely cancelled out and then some, as we just saw. The inline stop is ineffective for very similar reasons. The bus blocking a lane also has the effect of starving the bottleneck by impeding flow. Whatever the buses gain from not having to merge out of a pullout is offset by the ensuing delays that they suffer in the shared queues upstream. Only the offline stop, however nominally bad for buses we think it to be, conserves flow through the bottleneck. And as a result, it ends up being the best for buses, not just for cars. At the bottleneck, a zero-sum strategy just doesn't work. A bus-favoring policy cannot afford to hurt cars. The best thing we can do for both modes is to preserve car flow to the bottleneck using the offline stop. Having seen that bypasses are ineffective or even harmful near the bottleneck, we ask a new question. Does this bypass design work at all? To show that it does, we consider a scenario in which the bus stop is moved upstream to link 2. This is a hypercongested link, but one located a little further from the bottleneck. It turns out to be far enough upstream, at least in our setup, that voids do no harm. Of course, relocating our treatment doesn't prevent voids from forming. The bypass and the inline stop still impede car flows and still produce voids, as we'll show in this time-space diagram. However, those voids never actually reach the critical bottleneck at intersection 1. Instead, as you can see, they hit the backs of queues and get compressed before ever reaching the bottleneck. Thus, flow is maintained and no one is delayed. And the results of this are as shown here. We'll start with the inline stop, where buses dwell in a traffic lane and obstruct car flows, which we expect to be quite bad for cars. When placed on link 2, sufficiently far upstream, the inline stop produces excellent car performance. The average travel time that you see, 12.6 minutes, is as good as anything that we saw on link 1. Because voids are compressed, and the bottleneck is therefore not starved, the temporary obstruction of car flows by the inline stop doesn't matter. Buses thrive from this too. They avoid delays caused by voids, and they avoid delays caused by merging out of a pullout. The average travel time for buses that you see here, 13.8 minutes, is the best that we've seen yet. But we can do better by deploying the bypass. Whether buses are given 5 or 10 seconds of green, car traffic is still unharmed because voids are still compressed. Buses, meanwhile, fully benefit from the bypass. Each bus gets to skip ahead of the queue without causing cross-modal damage that would delay the buses to come, so that on the whole, buses average 0.8 minutes of travel time saved, relative to the inline stop. You'll notice I didn't show you numbers for offline stops. They're just not worth considering here. They are Pareto worsening. They impose a cost on buses by forcing them to merge out of a pullout without offering any benefit to cars. In the aggregate, what our findings show is that there is nothing inherently wrong with the AASHTO bypass. It can deliver the performance that it promises. It can be quite helpful to buses, as we see here. However, it has a crucial vulnerability. It should not be placed too close to a bottleneck in hypercongestion. The AASHTO guidance, as specific as it is, fails to caution practitioners against this risk. That is the main point of our paper, and we could end the talk here, but there are some additional findings that I think are pretty interesting. There are some scenarios where the bottleneck's capacity is extremely low. We find that this makes voids less harmful, so that sometimes buses benefit from a bypass even at the bottleneck. We also note that in a city, some links are longer than others. We find that cities can get a better return on investment by placing their bypasses on longer hypercongested links as opposed to shorter ones, provided that the bypasses are made proportionally longer to benefit. We further find that bypasses can be made more effective if they're deployed alongside a signal coordination scheme called backwards coordination, which is very suited to hypercongested conditions. We talk about all three of these insights in more depth in our paper. Now, to recap, our findings point to a clear deployment strategy for bypasses in hypercongestion using the AASHTO endorsed design. A bypass should generally not be placed on the approach to a critical bottleneck. If there has to be a stop located on this link, it should be placed offline in a pullout, but nothing more should be done. Upstream, any hypercongested link that has a stop is a good candidate for a bypass. Longer links with longer bypasses will yield greater time savings, but even short links make for good bypass locations. By deploying bypasses in this way, a city can significantly speed up buses, not by sacrificing cars, but by being mindful of them. The result is a Pareto efficient outcome. No one loses and buses benefit. Thank you.
Great. Thank you so much for the great presentation. I'm going to bring up the Q&A box. If anybody would like to ask a question, you have access to both the Q&A and chat window. We just look like we had several questions that were submitted during the registration process, so we'll go ahead and start with those. The first one says, is there any benefit to placing the stop immediately upstream of the bottleneck on link 2 as opposed to another hyper-congested link upstream?
I don't think so. There might be a marginal benefit just because the queue forms on link 2 a little bit earlier. But fundamentally, the question of whether a stop should be on link 2 or link 4 or anywhere else comes down to where the agency needs a stop to be as opposed to traffic factors.
Great, thank you. The next question says, are you proposing to relocate stops to different links?
Not really, no. A stop has to be wherever it has to be, and there's considerations that go into that beyond matters of traffic. If there needs to be a stop on link 1, then it has to be there. It should just be in a pullout. If the stop happens to be on link 2 or 3 or 4, then you should put a bypass there instead. Moving stops is just beyond the scope of our paper.
Okay, great, thank you. This next question says, was it assumed that the bus only signal or void happens every cycle, or was there consideration of only needing the signal phase when buses are present?
The assumption is that it only activates if a bus is present in the bypass at the start of the green. There's no real reason to waste time for a bus that isn't there.
Okay. It seems like some may be having challenges with the chat window. If you experience any issues with the chat window, please feel free to place the question in the Q&A box. Okay, let's see. Next question. Okay. Was it assumed that the bus only signal or void time was taken from the mainline phase, or was this taken from the street side?
Well, taking it
From the side street.
Yeah. Right. So we took it from the main arterial because taking it from the cross street would be a bit like cheating. We don't consider car traffic there. So theoretically, if we took green away from there, we could make everything better, but it would be disingenuous. Okay, there would be, in a real city, some scenarios where perhaps a side street might have more green time than it needs, and you could take green time from there. But we assume that whatever green time is allocated to the side street is the green time that it needs.
Great, thank you. It doesn't look like we have any additional questions. So I did place the evaluation on the screen. If you could take a few moments to complete the session evaluation, you can simply click on the link and or scan the QR code on the screen. Oh, it does look like we have one more question. It says, why have you not considered delay / person with consideration to the agents, excuse me, let me try that again. Why have you not considered delay person with consideration to the average bus occupancy?
Well, projecting bus occupancy and car occupancy is very region specific, city specific, whereas our findings show that what ends up being good for the goose is good for the gander. What hurts cars hurts buses. What helps buses helps cars. So, our findings show that putting the bypass upstream is good for buses and fine for cars. Putting the bypass downstream isn't even good for buses. So weighing by person hours wouldn't change that.
Okay. Okay, Nadav, it doesn't look like we have any other questions. Um, so again, on behalf of the National Institute oh, yes, the excuse me, the report as a and recorded copy of today's recording will be available on the NICER website. So I have provided a link to the NICER website on the screen. That will just take you to the list of upcoming and recorded webinars. But feel free to navigate to all of our upcoming um, webinars. Another question came in. It says, have you shared this report with ASHTO?
Not directly. It has been published in Transportation Research Part A and presented at the TRB annual meeting last year, but we haven't reached out to ASHTO directly.
Okay. Okay. Well, thank you so much, Naveed, for the great presentation today. So again, on behalf of the National Institute for Congestion Reduction, thank you so much for attending today, and we'll see you all real soon. Bye, everybody.
Thank you for having me. Bye, everyone.